incandescent spectrums, spectra which were continuums, reds blending into orange, blending into yellow, etc. And of course, the study of those spectra led Max Planck to his great discovery. During this study, several people, in particular I'd like to bring up Bunsen and Kirchhoff, started to burn chemical elements and noticed that the spectrum emitted by those were a discrete line spectrum. And each spectrum was unique to the individual element. So of course, we realize that means that there's some physics here. There's something about the physics that relates the spectrum to the chemical element. And that was very exciting, a very exciting idea. But people had a hard time trying to connect things together. So one of the things you do when you're in a situation like that is to simply guess at formulas that might fit the data. So in 1885, Balmer found the formula that fit the data for the hydrogen atom. That is, of course, 1 over lambda, the wavelength emitted, is going to be some constant which we call the Rydberg constant, times 1 over 2 squared minus 1 over n squared, where n can equal 3, 4, 5, and so on. Don't know why it works, but it works. Yes. You'll see in a few minutes. Anyway, the Balmer formula worked. It predicted each wavelength. And you guys have already measured the different wavelengths. For example, red being the longest wavelength happens when n equals 3. And then the next wavelength was a kind of a bluish, greenish color. And you put that wavelength in there and you put in n equals 4, and so on. Okay, we've got a formula. Can you reverse engineer the formula and figure out the physics from there? That was going to be our goal today. However, let me just fill you in on some more of the historical facts before we do that. Remember, 1900 is when Max Planck, studying the incandescent spectrum, postulated that atoms and molecules were discrete and diminutive electromagnetic oscillators, very small electromagnetic oscillators that oscillated with only certain frequencies, and gave up their radiation in little bursts, gave up their energy in the form of radiation in little bursts. By the way, this made Planck very uncomfortable. Why? Because the wave characteristic of light had been demonstrated both experimentally and theoretically long before. So he said, well, somehow these little discrete electromagnetic oscillators put out bursts of radiation, but they somehow link together and make continuous waves, as were shown in Young's experiment. Well, it was 1905 when Einstein was looking at the photoelectric effect, when he realized, no, that's not so. That the way that energy is delivered from atoms is in little quanta. It's not delivered as a continuous wave. So, in a way, Einstein extended Planck's work in describing the photoelectric effect, essentially describing the photon, this strange particle-wave duality that we call the photon. Now, let's move ahead. About 6 years later, 1911, a man named Ernest Rutherford. I'm simply going to refer to him as the father of the nuclear atom. He was the man that established nuclear structure. Prior to this, especially between Einstein, for the 6 years, from 1905 to 1911, people were trying to figure out, okay, we've got atoms and molecules, we know that they're made of electrons, mass, and positive charge, and what is the structure? Nobody knew. There was one fellow, J.J. Thomson, who proposed something we today call the plum pudding model of the atom. Of course, it's completely wrong, but I want to show you one thing. If the only thing you're aware of is that photoelectric effect ejects electrons, and what's left behind as an equal positive charge, the mass essentially hasn't changed. and those are the only facts you have to deal with, Thomson suggested that maybe the atom was a smeared out positive charge and mass with little electrons stuck in it, like plums in a plum pudding. And when light strikes the atom, it ejects one of the electrons, leaving behind all the rest of the plum pudding. Now, that's really not a bad analogy based on the limited information that he had. And physics always makes progress like this. You take your limited information, you create a model, and then you test that model. Well, it turned out the model was wrong. In 1911, Rutherford fired alpha particles at a thin gold foil nucleus, which, by the way, was only about 100 atoms thick. That's pretty thin. And if the Thomson model of the atom was correct, these little tiny alpha particles, known to be massive, small, and energetic, should go right through the target, almost like bullets through a paper target. He was taken aback to discover that, although most of them went through the target, a few of them actually were deflected at extreme angles. Now, how do you fire a bullet at a paper target and have it ricochet? Right? In fact, folks, some of them ricocheted so dramatically, not very many, but some of them actually bounced straight back. How could that be? Rutherford actually described it as, he said, I was as surprised as if I had fired a howitzer at a tissue paper target and had the bullet come back at me. Well, now we have these facts. Every once in a while, we get an extreme deflection of an alpha particle, sometimes even recoil of an alpha particle, but not too often. That suggested to Rutherford that atoms had very small, compact, dense, positively charged nuclei. And so when you're shooting at it, most of the time you miss the nucleus. It's so small compared to the atom, most of the time you miss, so the alpha particles go right straight through. But every once in a while, one of those alpha particles comes very, very close to that dense nucleus and gets deflected dramatically. 1911, Rutherford is the father of the nuclear atom. He discovered the atomic nucleus. Now we understand that the atomic nucleus exists as a very small, he was even able to estimate, a very small point charge and point mass, essentially at the center of the atom. What's the electron? Describe the electron. It took 2 more years to come around to a description of the electron. And first, let me tell you, of course, you're instantly wanting to say that, well, of course, we have this teeny little nucleus, which, by the way, is always drawn out of scale. The nucleus is 5 orders of magnitude smaller than the atom. 5 orders of magnitude. So, when you draw the nucleus even that size, the electrons would be orbiting at a distance greater than the size of this building. So we always draw this thing out of scale. And your temptation is to say, yes, the word I just used, orbital electrons, the electrons orbit. But there's a problem there, there's a classical problem there. That is, if an electron is orbiting, it's accelerating, isn't it? It's enjoying centripetal acceleration. It's been demonstrated that any time you accelerate an electric charge, it radiates energy. It was easy to show that if the electron was orbiting in a normal, standard, classical orbit, that it should radiate energy continuously and therefore spiral in to the nucleus. So atoms should radiate continuously and coalesce, get this, in 10 to the minus 8 seconds. That should be the lifetime of all atoms, 10 to the minus 8 seconds. Well, atoms seem to live longer than that, don't they? And they don't radiate continuously. So that's why people were sitting around and saying, oh my goodness, we've got a nucleus, we've got an electron, what's the electron doing? Orbiting? I don't think so. Because it's not doing these other 2 things, continuous radiation and coalescing. What's going on?
Does it 10 to the minus 8 have anything to do with the speed of light?
Say again?
10 to the minus 8 has anything to do with the speed of light?
Actually, it does, yes. And that's all I'm going to say right now. More later, though. That's why it took 2 more years. and the work of a brilliant man named Niels Bohr, who we today call the architect of the hydrogen atom. He's the guy that took all of the pieces, all of the bits and pieces of experimental facts and theoretical facts, put them together to understand how the hydrogen atom actually worked. So this was a powerful discovery, and I would like to pursue what he had to say now. Where am I? Well, I'll save the De Broglie waves for later. All right. So he said, let's for a moment assume that there is orbit. So he's going to put a nucleus here and an orbit like this. Now we're going to start out by talking about hydrogen, but please keep in mind that we're going to talk about any hydrogen-like atom, meaning simply a small nucleus with only one orbital electron. So you could make a hydrogen-like atom out of helium by simply singly ionizing it. Remove one electron and you've got one orbital electron. Lithium, just doubly ionize it. Get rid of two of the electrons and you still have one orbital. Hence, therefore, I'm going to say that the charge on the nucleus is Ze, where Z is the element number and E is the charge on an electron. And out here is an orbital electron who has charge E. It is a single electron. So, no, I don't do this now. So, let's begin by saying that the centripetal force is provided by the Coulomb force. So FCP, the centripetal force, is provided by the Coulomb force. That's where we're going to start. Now, if you're still worried about the classical radiation, don't worry, we're going to take care of that in just a moment. So centripetal force is mv squared over r. As you remember, if you have one point orbiting another point, the centripetal acceleration is easy to calculate. It's v squared over r. So centripetal force is mv squared over r. It's given by the Coulomb force. You probably recall it's q1 q2 over 4 pi epsilon naught r squared. Well, for us, Q1 is ZE and Q2 is E, so I notice there's an R in common, so mv squared equals ZE squared over 4 pi epsilon naught r. At this point, of course, you begin to concern yourself with the fact that, why isn't it radiating if we've got this going on? So, Bohr postulated once again, he said there are certain, and listen to the words that he uses, there are certain stationary orbits, whatever that means, stationary orbits, which is interpreted as orbits on which the electron doesn't radiate for some odd reason. And they are, the allowed orbits are related to certain angular momentum. So the angular momentum of the orbital electron, mvr, there's the angular momentum of the electron, as long as it is n times h over 2 pi. H, Planck's constant, divided by 2 pi, times n, where n is, what is the counting numbers, 1, 2, 3, and so on. So he's saying there are certain types of angular momenta which are allowed without radiation. If you ask me why, he said, hey, I just postulated it. I don't have to tell you why. It's postulate. I postulate that that's true.
Was it
Now,
true?
go ahead.
Was it true?
Yes. Would I be telling you if it wasn't true?
Yes.
Yes, I would. Yes. You're right. But it turned out to be true, yes. Now, let's see what are the consequences. And what we're doing right now, we're looking at the theoretical consequences to see if we can find anything that matches to an experimental consequence. Okay, so let's look at the theoretical consequences. And one of the nice ways of doing it is to solve this equation either for V or R. We've got two equations and two unknowns. The unknowns are the orbital velocities or the radii of orbit. So, take a moment, do the algebra, I'll do it on the board quietly, and reduce these two equations, one in terms of r and not v, the other one in terms of v and not r.
What's the numerator of the bottom equation?
What's the numerator of the bottom one? Is h, Planck's constant h. Is that what you're asking about?
Yeah, with the first
Yeah.
age.
Okay, I'll do it on the board quietly, you do it on your papers, please. Let's see. the two answers I got for velocity and R. Interestingly, notice that the requirement of quantized angular momentum gives us certain specific allowed velocities and radii. There is an infinity of allowed velocities because n can range from 1 to anything. And likewise, there is an infinity of R solutions because, again, n can range from 1 to anything, counting numbers-wise. So, great, we have a pretty good start on our theory then. We have quantized velocities and radii. Very often we subscript this with an n, and I'll give it a name a little later. So these are the certain allowed velocities and radii, keeping in mind that n can be any one of the counting numbers. Okay, that's great. So what are we going to do with this? How are we going to turn this into something we can test with an experiment? That's, of course, always the big goal in physics, is come up with something you can test, come up with a new idea that you can test in an experiment. And I think casting this information in terms of energy would be the wise thing to do. So what we're going to do now is write this in terms of energy and not just. You can't measure the radius of an atom, you can't measure the velocity of an electron, but maybe you can measure the energy of the thing. So, of course, the total energy that we're going to be discussing, energy total, is going to be kinetic energy and potential energy. You may assume B much, much less than C. Therefore, we'll just use classical formulas for potential and kinetic energy. Kinetic energy is easy. Now, kinetic energy. Notice, if you will, that if I come over here and simply divide this equation on both sides by 2, or multiply by a half, I have kinetic energy right here. So the kinetic energy is going to be ZE squared over 8 pi epsilon naught R. ZE squared over 8 pi epsilon naught R. And in a few minutes, we're going to substitute for R to find out which specific energies are allowed. But I'm not going to do that just yet. It just complicates things at this stage. The other thing I want to write down is the potential energy. And we're talking electric potential energy, of course, when you're talking about these kinds of masses, a proton and an electron, there's no gravity. So it's only electrical potential energy. You've got electrical potential energy and you've got 2-point charges. You might remember that the electrical potential energy is, well, first it's QQ over 4 pi epsilon naught R, but we get a minus sign out front, and QQ is ZE squared, and then we have 4 pi epsilon naught R. Interpret the minus sign for me, please. Why is it negative?
Because one of the charges is negative?
That's part of the reason, but what we say in physics, yes, the electron is negative, they're oppositely charged, so you've got a positive charge times a negative charge. That's a good mathematical answer, but in physics we say it's because the system is bound. You take a positive and a negative charge and they're held together. They're not repelled, they're held together. They're bound. It's a bound system. That's what the negative sign is. Or you can say algebraically it's because one charge is positive, the other charge is negative. Either way. Now we can write down the total energy. Energy total is going to be kinetic energy, ZE squared over 8 pi epsilon naught R minus ZE squared over 4 pi epsilon naught R. Obviously, I say, that then becomes minus ZE squared over 8 pi epsilon naught R. I'll write it again up here because I know I'm squeezing it down here. So energy total is minus ZE squared over 8 pi epsilon naught R. Now we've got the total energy of the atom, and I would like to put in the quantum condition. Here it is, right here. Let's put in the quantum condition for R. So now, what I'm going to call E sub n minus ZE squared, down here, 8 pi epsilon naught. And R is n squared h squared epsilon naught divided by pi m ZE squared, divided by pi m ZE squared. Aha! We've got some things we can combine, and we got one thing we can eliminate. The pi is gone. So now I'm going to write this as minus 1 over n squared. I'm going to take that quantum condition out. On top we have m z squared e to the 4th divided by 8 epsilon naught squared, 8 epsilon naught squared, h squared. And I think I've taken care of everything here. We've taken care of all of this here. Now there's the 8, there's the 2 epsilon naughts, the n squared, and the h squared. Aha! We now have an expression for the allowed energies in a hydrogen atom. Apparently, if our postulate is correct, and here's our postulate here, if our postulate is correct, anytime the electron is orbiting with one of these energies, it's a so-called stationary orbit. An orbit that does not radiate for some odd reason. Well, we're not quite to an experiment yet. We're almost there, though. We've moved towards an experiment we can do. Because if you have a hydrogen atom and it has certain allowed energies, let's imagine that that is the n equals 1, and this is the n equals 2, and this is the n equals 3, and so on. Let me label them n equals 1. Those are the stationary orbits. That as you move up in orbit, you must be adding energy. The energy difference between these orbits, for the electron to jump from this orbit to that, it cannot move, it cannot transition gently from n equals 1 to n equals 2. It must jump. First it has this energy, and then it jumps to that energy. That's a higher energy level, therefore you have to add that much energy, or you have to add this much energy. And of course, conversely, when they're jumping down, if it's jumping down from here to here, it must give up that energy. Or down from here to here, it gives up that energy, or for that matter, even down from here to here. All we have to do is to determine the energy gap. And that's the energy that the electron either has to absorb in moving up or radiate coming down. And of course, you see where we're going with this. We've been measuring energies as these things go down. As they jump down, the atom emits the energy in the form of photons. That's what we've been measuring. So our task now is to talk about the energy difference. Delta E, the energy difference, oops, wrong color. It's supposed to be right in the black. The energy difference is going to be, well, we're going to be thinking about transitioning down because that's what is radiating. That's what we're going to be able to experiment on. So we're going to be going from higher n values to lower n values, indicated like this. Look, my friends, the energy N2 minus the energy sub N1. So N2 simply means a higher n value, and N1 means a lower n value. As we're jumping down, that's what's going on, from higher n to lower n. Well, it's easy to write that down. Delta E, the energy difference is going to be 1 over N2 squared minus 1 over N2 squared times this creature, mz squared e to the 4th, over 8 epsilon naught squared h squared, 8 epsilon naught squared h squared, minus 1 over n1 squared, times the same thing, mz squared e to the 4th 8 epsilon naught squared, h squared. And so, of course, clearly it is just this factor out front. So we have mc squared e to the 4th over 8 epsilon naught squared h squared. That is the common factor that we factored out times 1 over n1 squared minus 1 over n2 squared. Aha! Aren't we getting around to something that is beginning to look a little bit familiar to you? We're not exactly to your experiment, but we're almost there, aren't we? All we have to do is to identify delta E in terms of wavelength. So the energy difference we're going to assume is the energy in the emitted photon. And of course, the energy in a photon is either h nu or it's hc over lambda. So delta E is going to be hc over lambda equals the same thing above. So let me just put ditto and ditto instead of writing it all out. And now we've got it, don't we? I think, yeah.
You transpose the 1 and the 2 subscript.
I did not. Notice that the n2 has a negative sign and the n1 has a positive sign. It looks like it, but don't forget the double negative. So, how do I go play on words on the double negative? There's no reason to worry about it. Okay. What am I doing? Oh, now you see I've got something. Just get rid of the HC, right? We've got 1 over lambda is equal to, oh my goodness, I don't remember. So what we're going to have is we're going to have an extra HC down below. So on top it's mz squared e to the 4th, mz squared e to the 4th, divided by 8 epsilon naught squared ch cubed. 8 epsilon naught squared ch cubed times 1 over n1 squared minus 1 over n2 squared. If we choose n1 equals 2, then n2 can equal 3, 4, 5. And our claim is that mz squared e to the 4th over 8 epsilon naught squared ch cubed is the Rydberg constant. The Rydberg constant, which was measured experimentally by you, should equal this. We have a theory that predicts a number that's measured. This theory is all predicated upon Bohr's model of the hydrogen atom. And lo and behold, now I can answer your question more specifically. Bohr must have been correct with his postulate because it turns out that this is the Rydberg constant. Let me ask you to take just a moment and calculate. Would you please calculate that? Show that this turns out to be equal to the Rydberg constant. To within your experimental limits, of course. Your experimental limits do not give you the precise Rydberg constant. But just show that. And most important, you know I'm going to get all excited, jump up and down, and stick my tongue out at you if you do not show units consistency. The calculation, that's a cakewalk. Units consistency, it ain't so easy. So the big thing here is to demonstrate units consistency. I'm going to start doing it on the board. Please don't watch me do it on your own.
Z are we using?
We're using hydrogen, therefore Z is
1.
I've forgotten the French word for one. Something like that. They have some funny way of saying it. Do any of you know French?
Nope. I used to.
Something like that. It's 2, but I can't remember one.
No, it's
You make Ed
Okay.
Yeah.
painful to speak French.
It is, actually.
It's like,
Bark style.
I'm sure in Christmas 5, you got that discussion of what did you say?
What does that mean? What the hell? Can you say it's gonna be something funny? Where's the beach?
Say what?
Where's the beach?
Say what? Say what?
What?
It just sounds like,
Almost sounds like queso.
it sounds like
I
quesadillas.
think,
Having spoken French is all I do.
How do you take in French in elementary school?
Dude, I had private elementary school.
That's kind of cool.
I know, right?
Man, I spent like an hour looking for Issa knot and it's in the freaking cupboard. Yeah, so much.
So that surprised you.
I mean, I spent an hour on the internet trying to figure out what Epsilon was.
And the internet also didn't count. That's weird.
Yeah, for some reason, like, there's more Epsilon knots for other fields of science.
But that's the productivity.
Yeah, it took
The
a while.
internet's like, okay, you're, that's not cool, man.
The internet failed me. That's okay. I can live in it.
Wouldn't surprise you. It's not the first time.
My 6 comes in at 19 for the charge. third.
That's Fahrenheit.
I can't remember what it breaks down into though.
It breaks into coulombs per volt. Volt is joules per coulomb.
So,
Circuits.
it's equal to 1 over
Where's your teacher?
1 over.
I generally don't go around breaking farads into the things.
Well, let's go fundamental.
That's a good one.
Right? kgs squared meters to the fourth.
Generally, it doesn't do anything. So generally, doing that doesn't do anything.
What's triggered?
Yeah, meters per second here. And we have kgs squared meters to the sixth over seconds to the third. Boy, this is something. What fun. So, get rid of some more stuff. Kilograms squared. Kilograms squared. That's gone. Let's just combine these, turn it over just to make it a little bit easier. Make life a little more obvious. 1 over, what I say, we'll combine these two. So it's going to be seconds to the fourth over meters to the sixth. That's this thing inverted. But yet still down here. Here's the meters per second. And here's meters to the sixth over seconds to the third. Aha, the seconds are gone, aren't they? Seconds are gone. And most of the meters are gone. We end up with 1 over meter. Was that fun?
Math isn't working as far as.
Some people
The
say
numbers.
Yeah.
All right, we got the units to work, that's the hard part. Now comes the number. We got the units to work, let's do the number now. Let's see. So, we have, where am I gonna write? I'll write way to there. Just because I got more light on the board over here. So we got 9.1 10 to the minus 31. Times 1, so we'll just forget that. 1.6 times 10 to the minus 19. 1.6 times 10 to the minus 19. 4 divided by 8 times 8.85. 8 times 8.85. We decided that was times 10 to the minus 12, right? And that is squared. And we have 3 times 10 to the 8. And finally, Planck's constant, right? We have 6.63 10 to the minus 34. 6.63 10 to the minus 34 cubed. And this is all 1 over meters. Cubed, squared, upstairs, we have to the 4th. So, 9.1 times 1.6 times 10 to the 5. Minus 80, minus 76, minus, is that 107 on top? Downstairs, we have 8 times 8, 1.85 times 3 times 6.63. This one is cubed, this one is squared. And we have times 10 to the what? 10 to the minus 24. 10 to the minus 58. 10 to the minus 50, do I get that right? Yeah, minus 50. Check my arithmetic, if you would, on these two numbers here. Is that a minus 107? Is this a minus 50? Because I just did the arithmetic in my head, and believe me, when I do arithmetic in my head, it's really suspicious.
I do hope it's gonna be like it's suspicious to you.
Isn't C also squared? This is
Look, I did not, not do that.
What?
Comes out to be about, I think it's 118.
I'm glad you got that. Now, let me see, minus 24. This is minus 9.
I know, but I'm saying when he transfers
Yeah,
it there,
minus
he just says 1.6.
19 plus 112, well, 102, that's minus 102. I think that's right.
I see what you're
I
saying.
think that's right.
Yeah, she's
And
right.
that's much better. That looks
I
much
think you're
better.
right.
So when I bring that up, it's what, minus plus
11.
C,
you are.
that's 11 plus 11. Okay, so now all we have left to do is what's in the square bracket right here. Uh-oh.
You can-
Four.
That's okay.
So all we have left to do is what's in this. That's what you do with your calculator. If you were trying to stick the numbers in at this point, it might have gotten really ugly.
Yeah, it doesn't.
Yeah.
And your calculator might have had a, what do they call it, frame bark? Because of those high powers of 10.
This is
Comes out right then. These are the kinds of things you should check. When people say to you, that is the Rydberg number, you should check it. This is one of the things you do when you're studying at home. You say, I'm going to check that units and number. You don't say, oh, the teacher says it's the Rydberg number, so it's the Rydberg number. I have lied to you in the past, haven't I? And I shall continue to do so in the future. So check this stuff, and it's not easy. In other words, ladies and gentlemen, the experiment that you did on Monday is one small confirmation of the Bohr model of the hydrogen atom. You didn't know that then, did you? Well, you're all happy and smiling about that, and I'm glad because I have a handout for you, and this will help you finish your lab. So let me quickly get this out to everybody. There's 3 of them here, 3 of them here, 1, 2, 3.
doesn't check out.
2. And at least as important as the laboratory itself is the theoretical derivation, which is on this paper. You watched me do it on the board. I'm glad you took very nice notes watching, but these will complete your notes. The hydrogen spectrum and the Rydberg constant. You'll notice that it starts out with a couple of pages of theory. It shows the Balmer guess on the first page. The second page and most of the third page really is the theory that we discussed. And then they show the nice transition states, which represent hydrogen, showing from the n equals 1 orbit all the way out to the n equals 7 orbit. Now you can see that the visible spectrum produced by hydrogen happens when electrons are cascading down from higher n values down to n equals 2. There is also a transition from n equals 2 to n equals 1, but that energy transition is so large and is shown to you relatively accurately on the next page. That energy transition is so large. Is everybody on the next page where it shows figure 116 energy level diagram for hydrogen?
Yeah.
You can see that jumping from 2 to 1 is relatively accurately depicted here. That's an extremely large energy transition compared to all of the others in the Balmer series. That what would you expect? Would you expect it to be visible or what? Huge energy transitions compared to everything else. So it's not going to be visible. What's it going to be? Ultraviolet, yes. There's going to be a strong ultraviolet. You know what? Nobody knew there was an ultraviolet spectrum to hydrogen until this theory came out. Here's another very important aspect of good science. Not only does it confirm the experiments you've done, it makes predictions that can be tested. So we have a very specific predicted ultraviolet spectrum here. They name it the Lyman series. We can very accurately calculate a precise ultraviolet spectrum that should exist if Bohr is correct. And there it was, ladies and gentlemen, there it was. Exactly as predicted. So you can see this was really a triumph of the early part of the 20th century. It described everything we had seen to this point. It made some predictions never seen, and the predictions were accurate. Let's see what the next page is. The next page is, oh yes, everybody was always asking me about who this Rydberg character was, so a student a few semesters ago found this little description of Rydberg that was kind of interesting. And then another student was interested in the angstroms, so the next few pages are a description of the angstroms. So that's just there for your edification if you care to read it. All right. So we have the hydrogen spectrum and the Rydberg constant, which was a great leap forward in early 1900. This was 1913 when all of this took place. Very, very exciting event. It's kind of curious that it took so long before we made the next significant step. And I'd like to talk to you about that right now. First off, I want to tell you about the character. His name was Louis de Broglie. A French lad going to the university in Paris, and eventually changed his major to physics. The physics department was delighted. You know why? De Broglie was from a wealthy family. Not only was his family paying his tuition each semester, but they were granting a lot of extra money to the physics department. So you can imagine the physics department liked young Louis. And were quite encouraging for him to stay on in graduate school, which he did. And it was, when he had finished his graduate classes, it was time for him to write his thesis, come up with a new independent idea that he could support theoretically. And he came up with a very interesting idea. That is, he noticed that 19 years earlier, Einstein had claimed that anything that has a wave property to it should have particle properties to it as well. I'm thinking particularly the photon. The photon, which we knew to be a wave-like thing, light waves coming out, carried momentum with them, and that's the particle characteristic. So, in those early days then, the momentum of a photon, which of course is the energy of the photon divided by c, remember it's the quote massless particle, could certainly be written as h mu over c. So there's the momentum. But the frequency of the photon is easily written down as the speed of light divided by lambda according to wave theory like that. So our new momentum then is going to be simply h over lambda. So, interestingly enough, de Broglie said, well, here's what Einstein said, that a photon which has a wavelength lambda carries momentum with it. And that was a big surprise in 1905. That was 19 years earlier. In 1905, the big surprise was it's got a wavelength and it's got momentum. He says, why shouldn't we just assume that the reverse is true? That is, anything with a momentum has a wavelength. So, light waves have particle characteristics. Why wouldn't particles have wave characteristics? A perfectly symmetric argument, which of course is utterly absurd. But you know what? The physics department had a real dilemma on their hands. To begin with, his thesis was very, very thin, and secondly, the thesis was absurd. Now they've got a problem. You know what their problem is? If they deny the boy his PhD, then the family cuts off the money. If they give the lad his PhD, the world will be laughing at them because they gave a PhD on such a ridiculous premise. They've got a problem, don't they? The traditional rock and hard place, huh? Of course, physicists are pretty smart, so you know what they did? They packed up de Broglie's thesis and mailed it to Einstein. Why? Einstein is the god of physics by this time. He's the god of physics. And so they'll mail it to Einstein. Einstein will send back a letter saying, this is ridiculous. They can take the letter to the boy and say, look, we like you. But Einstein doesn't. Not us. It's Einstein denying you your degree. So that way they wouldn't have to take the blame, would they? Pretty clever. Good idea. You don't like this? Send it to God. They were really surprised when Einstein wrote back and said, brilliant, give him his PhD. What? Yes, brilliant, give him his PhD. Really? Well, let's start talking a little bit about this. Anything with a momentum would have a wavelength. So lambda is equal to h over mv. Do remember, m equals m naught gamma. So there are some relativistic effects that may have to be accounted for from time to time. In-class de Broglie waves, I've got a problem for you to solve. An in-class problem.